Hello, welcome everyone. This is the second session of Theme 1 under our IWRA Online Groundwater Conference. And this is Groundwater Resources Assessment under Climate Change, Natural Resources Assessment under Climate Change. I am one of your co-chairs, so my name is Richard Taylor from University College in the UK, and my co-chair is Renée Martin-Nagle, who is the IWAR treasurer. And Renée, you are based currently in, are you in Philadelphia or Pennsylvania?
I'm in Pennsylvania, yes.
Pennsylvania, okay, very good, very good. We had a lovely first session earlier today, and we're looking forward to the speakers, including our keynote speaker, Professor Bridget Scanlon from the University of Texas at Austin. Just one reminder for the speakers: if you can keep to under 10 minutes, that will allow us perhaps a minute or two of questions that may be some quick clarifications before your immediate talk is over. We will also field questions at the end in a plenary. I guess I will now hand over to my co-chair, Renée. Renée, I believe that we can, it's 15 minutes actually for Bridget's keynote presentation, and I believe
yes,
Bridget is ready.
She's here. Yes.
Okay, do you want to introduce Bridget and we'll get started?
My pleasure. Hello, Bridget, and hello to everyone. Bridget Scanlon is a senior research scientist at the Bureau of Economic Geology in the Jackson School of Geosciences at the University of Texas at Austin. And Bridget, if you're ready, we'd love to hear your keynote speech.
Sure. So I'm going to talk about impacts of climate extremes and human water use on groundwater resources in major aquifers in the US using gray satellite data and modeling and monitoring data. And this was a part of a study integrating NASA scientists with the US Geological Survey and academia. And I have a number of co-authors that I would like to acknowledge. Next slide, please. So I'm going to try to address three basic questions. How is total water storage changing in these aquifers? Is it increasing or decreasing or remaining stable over the past 1.5 decades since we've had GRACE data? And then what is causing the trends in water storage? Is it climate extremes? Is it human water use, or is it both? And then how can we use the results from these studies to try to advance more sustainable water management in the US. Next slide. So many of you may be familiar with the GRACE satellite, so I'm not going to spend much time on it. Basically, these satellites, by monitoring the distance between the satellites, we get estimates of Earth's gravity field, which is controlled primarily by variations in water storage. And these are linked to floods and droughts and ice melt. I'm going to focus on the first mission, GRACE mission, with the data from 2002 through 2017. And we will use total water storage from GRACE data, which includes surface water, soil moisture, and groundwater. Next slide. So here you can see the major US aquifers, and we are very fortunate in the US to have a lot of large aquifer systems. And I guess I don't have a pointer, but in California, in the West, the Central Valley system, large alluvial aquifers, Columbia Plateau and Snake. In the Northwest, basalt aquifers, very thick basalt aquifers. And the High Plains system is also a huge aquifer system, and the Mississippi embayment, and other large aquifer system. And the US, the western part of the US is pretty arid, semi-arid and arid, and the eastern part is more humid. Next slide. So Lenny Conoco has done studies over a number of years looking at water storage changes over the past century. And these are the numbers that he came up with from 1900 through 2008. And you can see the Central Valley minus 145 cubic kilometers over this time period. Arizona minus 102, the High Plains system minus 340, and the Mississippi embayment minus 180. And you can see rises in storage in the Northwest up to 40 cubic kilometers over this time period in the Snake Plain, and much smaller changes in other regions. So these are the main hotspots of groundwater depletion: the Central Valley, Lower Colorado, Arizona, High Plains, and Mississippi. Next slide, please. And next slide. So going to talk about the results. So here you can see the trends in total water storage from 2002 through 2017. And you can see similarity with the work that Lenny Conoco had developed previously. So the reds show depletion in storage, mostly focused in the southwestern US and central and southern High Plains and Texas region. So this entire region shows depletion in storage over this time period. And even within a single basin like the Central Valley, you can see larger depletion in the southern part of the Central Valley, minus 22, versus much lower depletion in the north, which is more humid, about minus 9 cubic kilometers over this 15-year period. Similarly, in the High Plains, people often talk about the High Plains depletion and stuff, but you can see the northern High Plains, mostly Nebraska, increases in storage and declines limited to Kansas and Texas region. Mississippi embayment, very little change in storage from the GRACE data, which does not agree with what the regional modeling results from the USGS that Lenny Conoco pulled together. So I'll just show that slide one more time to show the difference in the Mississippi embayment. Next slide, please. So you can see minus 64 cubic kilometers over an 8-year period from the regional groundwater modeling for the Mississippi. And this GRACE data suggesting that there's very little change in this region. So we'll talk about why there may be a discrepancy shortly. Next slide, please. So now I'm going to show a time series of total water storage and compare with the climate forcing. And so here the black line, this is an example basin in the Southern Central Valley, or the Northern Central Valley Sacramento Basin. And you can see total water storage time series from 2002 through 2017. And the gray bars in the background are cumulative precipitation anomaly. So you can see increases in storage during wet periods and declines in storage during drought, 2007, 2009, and 2012 through 17. And on the lower plot, you can see the US drought monitor data, yellow showing just dry conditions and the extreme red showing exceptional drought. So you can see the total water storage generally corresponding with the drought periods and the increases in storage and recovery during wet periods. Next slide. So here you can see, I just showed you the data for the Northern Central Valley, the Sacramento Basin, and the Southern Central Valley is similar but more extreme. And I think what's interesting here from the US Drought Monitor is that the drought ended, the 5-year drought ended overnight with atmospheric rivers in January 2018. So the ends of droughts are oftentimes marked with floods. Next slide. And the Arizona alluvial, the Southern Colorado Basin, you can see it's been subjected to droughts over most of the period and the declines in storage over this time period. But not as intense droughts as we saw in the Central Valley. And also in the Central and Southern High Plains, extreme drought in 2012 through 14 and a greater depletion in total water storage over that time period. Next slide. And then in contrast, then the northern high plains, you can see the total water storage change corresponding to wet and dry climate cycles, but an overall increasing trend. So less intense drought in the northern high plains, a shorter time period, and an overall increase in storage, but linked to climate. Next slide. And then in the northwest, we don't really see a great correspondence between total water storage and drought periods in the Snake or the upper Colorado River, like we saw in the southern Colorado. Next slide. And in the humid eastern region, then you can see very little drought and then slight increases in storage in many of these basins. And next slide. And then drought corresponding and corresponding total water storage changes in the southern Texas region. So next slide. So here you can see the cumulative drought severity index, which is calculated by weighting the different drought levels from the US Drought Monitor. And you can see the numbers are low in the humid region in the east and much higher in the southwestern US, where they're more prone to drought. Next slide. So we've just talked about climate impacts and see good correspondence in most regions between climate, drought and wet cycles corresponding to total water storage. And now I want to talk about human water use and focus on irrigation. So here you can see irrigated land use in many of the basins. You can see the Central Valley, the Columbia, the Snake River Plain in the northwest, the High Plains, the irrigated regions, and the Mississippi embayment. So next slide. So when we looked at human water use, then we compared the data for 2010 and 2015. And here I'm showing data for the Southern Central Valley. So the light blue is surface water sourced irrigation, and the dark blue is groundwater irrigation, and the gray is other water use sectors. So many of these regions are dominated by irrigation water use. So 2010 was a wet year, 2015 was a dry year, was the middle of the extreme drought. So you can see that water demand did not increase during the drought, but actually decreased by about 30%. And the source of water for irrigation changed. So a decrease in surface water, which is piped from the north, and an increase in groundwater. So we went from 30%, 70% surface water during wet periods to 30% surface water during droughts. So this change in water source has a big impact on water storage. Next slide. So in the northwest, we have a lot of surface water use in the Snake Plain and the Columbia Plain. So this might explain the increasing trends in water storage, because inefficient surface water irrigation recharges groundwater, just like managed aquifer recharge. Next. And we just looked at the California area and the San Joaquin Tulare region, just talked about that. Next. And Arizona alluvial basin, we have almost equal volumes of surface water and groundwater irrigation, and not really much change over time because it was in a continual drought. But in the upper Colorado basin, it's nearly all surface water. So that may explain why we don't have very much depletion, because there's very little groundwater use. Next. In the northern high plains, there is some surface water from the Platte River, but not very much. It's mostly groundwater. But in the central and southern high plains, there's no surface water for irrigation, and that may explain the continued depletion and mining of groundwater. Next. Very little irrigation in this region here in Texas, so it's all basically climate driven. Next. So this is surprising, the Mississippi embayment. Look at the groundwater use for irrigation in this region is huge, even relative to California, and still we're not seeing any depletion in water storage. And we think this may be related to the fact that the groundwater pumpage is capturing surface water and not depleting storage. And they're doing a lot of geophysics now to look at the connectivity between surface water and groundwater. Next. And lastly, very little irrigation in the humid eastern region, and so that may explain the storage changes. So next. So then how can we move towards more sustainable water management? And so this will depend on the type of aquifer system. When we have access to surface water and groundwater, we need to conjunctively use them and use the surface water during wet periods. And inefficient surface water recharges groundwater, just like managed aquifer recharge. And we see this in the Columbia Plateau and the Snake River Plain in the Northwest. And that may explain the increases in total water storage. We can also use managed aquifer recharge, which they've been doing in parts of the Central Valley for decades. The Northern High Plains, Arizona alluvium, they've been taking water from the Colorado and irrigating with it recently. And the Mississippi embayment may be capturing surface water just because of the connectivity between the two systems. And when we don't have access to surface water, as in the Central and Southern High Plains, I think the only thing we can do is use extremely efficient groundwater pumpage and reduce irrigation pumpage to extend the lifespan of the aquifer. Next.
So Bridget, can you wrap up in 1 minute?
Yeah, I can. So there's a lot of interest in capturing surface water and recharging groundwater. And so in this slide here, I show full surface water reservoirs in Texas and depleted aquifers. So we're now trying to capture some of that and recharge these depleted aquifers. Next. So in summary then, total water storage is decreasing in the southwest and south central US, but is stable or rising throughout the rest of the US. And the causes, climate plays a major role in controlling water storage changes, but these storage changes from climate are amplified or damped by human water use, depending on the source of the irrigation. Next. And then we just talked about how we can make it more sustainable. And next. And would like to acknowledge all the other people that worked on this project. I'm very grateful for the opportunity to do this. Thank you.
Thank you, Bridget. That's fascinating, really fascinating. I'm sure there's going to be lots of questions, and we don't have time to take any at this moment, but we have a plenary at the end of this session in which we can debate some of those questions raised in the talk. Renee, could you please introduce the next speaker then?
Yes, Jana Levison, it's your turn. Jana is the Associate Professor, Water Resources Engineering and G360 Institute for Groundwater Research in the School of Engineering at the University of Guelph. So Jana, we look forward to your presentation.
Thanks very much for the introduction. As I start, I'd like to acknowledge my colleagues that I worked on this research with from UQAM, Marie Larocque, Sylvain Gagné, and Shoaib Salim. I'm going to provide an overview of a subwatershed-scale investigation of climate change impacts on groundwater quantity in an agricultural setting. Next slide, please. The goal was to identify future opportunities and challenges for agricultural production enhanced or limited by groundwater availability in water-stressed aquifers. We need to better understand the long-term source availability considering climate changes. We focused on the local scale to examine the stress a small subwatershed can experience based on multiple competing uses to ultimately provide information for watershed management. Next slide, please. Field research was carried out in a 65 kilometers squared study area, 120 kilometers southwest of Toronto, Canada, essentially in the space between the Great Lakes, so Lake Huron, Lake Erie, and Lake Ontario. We examined a portion of the lower Whitemans Creek, a subwatershed of the 6,800 kilometer squared Grand River watershed. This site is instrumented with 12 monitoring wells, 5 surface water stations with a water survey of Canada gauge at the outlet continuously recording flow. Water flows generally from west to east towards the Grand River, which ultimately discharges into Lake Erie to the south. The main superficial aquifer resides in the Norfolk Sand Plain, consisting of medium to very fine sand. The increasing water demand for agricultural production and maintenance of ecological features has led to the classification of the lower Whitemans Creek subcatchment as an area of water use conflict. A further reduction of flows in the creek could be problematic since it is an important for cold water fish, for example. Land use is primarily agricultural, over 70%, and the primary crops are corn and soybeans, with specialty crops that include sod, ginseng, and vegetables. This used to be a major tobacco production area, but that has declined quite a bit in recent decades. Low water advisories have been more frequent in the past years. In the province of Ontario, permits to take water are required for groundwater and surface water pumping exceeding 50,000 liters per day. The Permit to Take Water program is not an allocation of water, it's a permission to use water in the province. In 2016, where we did most of the field work for this research, the Lower Whitemans Creek had 47 active permits to take water for pumping the aquifer, ponds, and the creek, with all but 2 of these permits issued for agricultural use. Next slide, please. The field study comprised examining groundwater surface water interactions using stable isotopes, electrical conductivity, and radon-222. A conceptual water balance was done, and we examined some longer-term data available from 1960 to 2017, including flow at the outlet, precipitation, temperature, and permits to take water. Next, please. The historical and newly collected field data were used to construct and calibrate a flow model using SWAT ModFlow, which combines the land surface and stream hydrologic processes of SWAT, which stands for Soil and Water Assessment Tool, with the groundwater hydrologic processes of ModFlow to provide a comprehensive coupled hydrologic model for watershed systems. The model was calibrated based on surface water flows from 1960 to 2017 and groundwater elevation data from 2007 to 2017. 10 contrasting climate change scenarios based on RCP 4.5 and 8.5 provided by Oranos Consortium after a cluster analysis based on temperature and precipitation changes were used to evaluate the potential impacts of future climate change on the water balance. These scenarios represent a wide range of trends in seasonal temperature and precipitation. The reference period for the SWAT ModFlow modeling was 1971 to 2000, and the future period we simulated was 2041 to 2070. Next slide, please. These are components of the water balance in millimeters over the subwatershed for observed and future conditions. Fute 1 is 2041 to 2017, and Fute 2 is 2071 to 2100. But note that only the 2041 to 2070 period was simulated using SWAT ModFlow, the results of which will be in following figures. The first 3 dark blue circles are for observed and future precipitation, which increases in the future. The next 3 green squares are observed and future potential evapotranspiration, which increases. The next blue circles are PNET, or net precipitation, P minus PET, which increases for 2041 to 2070, then decreases for the late century period. The orange triangles, SD, are observed and future summer deficits, which is precipitation minus PET for June, July, and August, which increases in the future. The light green square is actual evapotranspiration, which we calculated from precipitation minus the flow at the creek outlet from 1960 to 2017. The next light blue circles are recharge from hydrograph separation over the long-term record and from difference in flow rate between the inlet and outlet during the field study, respectively. And finally, in the red diamonds, we have QP allowed, which is the water permitted to be pumped via permits to take water from 1962 to 2016. And QP declared is the amount reported by permit holders to be taken from the provincial water taking reporting system. And that data was just available from 2005 to 2016. Although the declared pumping rates are quite low, a very important finding is that the permitted pumping amount is similar to the recharge estimate, which could be very problematic if everyone starts using the amounts permitted by the province. Next, please. The next figure on the top right shows recharge determined using the SWAT ModFlow model, comparing the ensemble of data for the reference period, P in green, to the future period, F in blue, for each month. A and B indicate the results are significantly different. Recharge will significantly increase in the fall and winter months with earlier snowmelt anticipated. The lower figure shows results for water elevations in one monitoring well as an example of model output. Groundwater elevations are expected to increase in most locations and for most months in the future. We also calculated a vulnerability index, which is not shown here, but although more future precipitation is anticipated, evapotranspiration also increases So the system is also expected to be more vulnerable to water deficits in the summer months in the future. Next slide, please. Using this approach, it is possible to identify future opportunities and challenges for agricultural production enhanced or limited by groundwater availability in a stressed aquifer. Overall, for the Lower Whiteman's Creek, the groundwater system appears to be fairly resilient to climate change impacts, and the results suggest that there are several opportunities for agricultural production, such as increased pumping for irrigation, based on overall increased water availability in the future. However, some challenges may occur due to the already stressed nature of the study area and due to the timing of future water availability in relation to critical timing for agricultural production. In general, there will be more water available, so recharge, stream flow, base flow, groundwater elevation in the subwatershed in winter and fall seasons. However, it's anticipated that there will be less recharge and stream flow available during the summer months, which is a critical period for crops. Finally, we would like to point out that long-term monitoring of all hydrologic components is essential to better understand stress watersheds and how they may be impacted by climate change. Next slide, please. In closing, I'd like to acknowledge all of the partners and funders for this project. Thank you very much.
Thanks, Jana, for your presentation. That was very clear and good timing. I think we have time just for one question at the moment, or perhaps two. There's one in the Q&A that's come up, and the question was, what about the assumptions around the quality of the pumped groundwater and its and the possibility or any, and it's I guess the resilience of that quality. Will it be suitable? Are your assumptions valid that it'll be suitable for agriculture?
That is an excellent question, and that's something that we're actually hoping to start investigating in our next phase of this project. So we're going to be looking hopefully at nitrate and phosphorus in the system. We have done some preliminary measurements, and there is high nitrate and some high phosphorus levels as well. So we just want to, we need to investigate that more, especially with the increasing in recharge values that might be an issue for the nutrient quality for sure. So it's a good question.
Yes, have you identified any potential risks within the catchment itself at the moment to quality?
Well, yes, we have, it's predominantly agricultural area with it's 70% agricultural, 50% of the land area is in corn and soybeans, so corn gets very high nutrient applications. There's also a golf course in the area which applies nutrients, and there's also a town that's on septic and wells. So that is a potential risk that we haven't looked into as much. We were focusing more on the agricultural part, but we're hoping to look at that more next.
Okay, great, thank you. Maybe road runoff as well, but anyway.
Oh yes, that's a good point.
with the salt loading. Anyway, we'll take up more of that in the plenary. I have an apology to make to Bridget. I somehow got confused with the timings, Bridget, and we'll have 5 minutes more for your keynote for questions toward the end. Renee, I think it's time now for us to move on to the next speaker, and I was wondering if you could introduce the next speaker. Thank you, Jana.
Yes, of course. Chinchu Mohan is going to speak with us next. Chinchu is a postdoctoral researcher at the University of Saskatchewan, and I have to note that the University of Saskatchewan is where our keynoter from yesterday hails. That is Jay Famligeti. So please, Chinchu, we look forward to your presentation too.
Thank you for the introduction. Before my talk, I would like to acknowledge my colleagues at University of Saskatchewan, University of Victoria, and University of Melbourne for helping me with this research. So good morning, good afternoon, good evening to everyone, depending on whichever time zone you are in. So today I will be talking about the uncertainties in groundwater recharge under climate change. Next, please. Undoubtedly, we all can agree that groundwater is a very crucial natural resource which needs a scientific undertaking, but unfortunately, compared to other aspects of the hydrosphere, groundwater's relationship with climate change is least understood, and the uncertainties involved in making such a study is not well established. Next, please. One more click. So we decided to study the climate relationship with groundwater by studying the groundwater recharge, which is the connector between the above and below water worlds. Next, please. So in order to address this objective, we chose few global climate models. Next, please. So we were particularly interested in the precipitation and the evapotranspiration. Evapotranspiration was not readily available, so we used the Penman-Monteith method to calculate it. Next, please. So these two outputs were bias corrected using the quantile technique using some standard data set. Next, please. One more click. And this bias corrected climate inputs were forced into a empirical recharge model, which we developed, which runs at a 0.5 degree resolution at the equator at an annual time step. Next, please. We used 2 different GCMs and 2 different RCPs and 3 different ensemble members for each of this case, where the ensemble members are only differing at the initial condition, which means that the model physics and the initialization process, everything remains same. Only the starting of the model run is different. So ideally, the results from the ensemble members should be very similar to each other. So we've got very curious to see whether that's true or not. Next, please. So from our results, we found that irrespective of the GCMs or the RCPs, the global mean groundwater recharge was increasing, having an increasing trend across the next century. This doesn't mean that the groundwater recharge is increasing uniformly. Next, please. So in order to look into the homogeneity of the groundwater recharge trend, we looked at the spatial component of it. So this map shows the percentage change in the groundwater recharge till if you compare the current condition with the 2080 condition. And the red or the yellow to red region shows a decrease in the recharge, and the green region shows an increase in the recharge. And we can see that there are lots of like yellow to red patches in all the 4 maps. And we found that approximately 38% of the entire land area is having a decrease in the recharge. And unfortunately, some of these regions are coinciding with the hotspots or the overused regions and ecologically important region. So one of such ecologically important region is the Amazon region, where we found that approximately like 40 to 70% of the recharge is decreasing by 2080. Another very interesting result which we found from these maps are, so if we compare different GCMs and different RCPs, we are having different trends. And more surprisingly, so the different frames that are coming in each maps are results of different ensemble members, which ideally should be the same, but it's not. So I would like to draw your attention to Australia, especially in the MPI 45 map and a HADGEM 85 map. We can see that the colors are switching from green to yellow, which means that it is changing from a negative trend to a positive trend, which is very contradictory. So the first 2 kind of uncertainty, that is the uncertainty between the GCMs or between the RCPs, are well addressed in the literature comparatively. So we digged a little bit deep into the uncertainty between the ensemble members. Next, please. So this map shows the coefficient of variation between the ensemble members in percentage. So it clearly says, it's clearly seen that the southern hemisphere have a dominance in the uncertainty compared to the northern hemisphere. Next, please. And we also found that with percentage change in the recharge, whether it is an increase in the percentage or decrease in the percentage, we found that the coefficient of variation, that is the uncertainty between the ensemble members, was increasing. Next, please. So using all these uncertainties, we ranked the catchments based on the uncertainty or the coefficient of variation between the GCMs, between the RCPs, and between the ensemble members, with rank 1 being the maximum coefficient of variation, which is the highest uncertainty, and rank 25 being the minimum coefficient of variation. So if you look at the one of the most overused aquifer of today, which is the Indo-Gangetic Plain in the northern part of the Indian subcontinent, consistently it is having a higher ranking, which means it is having a very high uncertainty. And also, if you look at the lowermost figure, where the uncertainty of ensemble between the ensemble members, which is most ignored in most of the studies, the California Basin, the Great Artesian Basin, and also the Indus Basin is having very high uncertainty. The implication of this is we are ignoring this uncertainty and we are moving forward and making a plan for the future. And we are actually missing on the catchments which need to be taken care of, or more care need to be given. Next, please. So in conclusion, we found that the groundwater recharge was increasing, but that doesn't mean that we are going to have a better future, because it's not uniformly increasing and the hotspots are still in danger. And also we found that we have a lot of uncertainties, that is between the GCM, between the RCP, and even between the ensemble members, which are often ignored. But we found that between the ensemble member uncertainty are also comparable with the previous or the prior to uncertainties. Next, please. So with all this uncertainty, the question we are facing, or the challenge we are facing, is how good are the insights we have into the future, and how are we going to prepare ourselves for that coming future? Next, please. So the recommendation we have is, it's for sure that we cannot make a perfect prediction for the future, but what we can do is to include maximum uncertainty into our analysis. So previously, or the conventional way is to use a single ensemble member or a average of multiple ensemble members and do the analysis. But what we are suggesting is that's not enough. So we have to include multiple ensemble members in our analysis so that we can get a better idea about what is there for us in the future. Next, please. Thank you.
Thank you very much, Ginger, for your presentation. We have probably time to take one question that was that's been posed in the chat box, which is a question about the empirical recharge model that you used. What is it exactly? Is it a kind of process-based one? Or what? Yeah, can you just explain a little bit, what is the empirical recharge model that you're describing?
Sure. So that recharge model, it's not process-based. It's a data-driven recharge model, which we developed using the metadata analysis method. So we collected like 715 recharge estimates from all over the world, and we did some quality control, and we made a multi-regression analysis and build a model. But I have to acknowledge that there are some limitations to the model. So the next step of the analysis will be to extend this to, process-based global hydrological models and see like whether this really holds good.
Okay, thank you very much. We'll take up some of the other questions that have appeared in the plenary session. So thanks very much, Ginger. We'll move to the next speaker now. And Renee, could you introduce the next speaker?
Yes, the next speaker is another early career researcher. Mary Hingst is a PhD candidate at the University of Delaware. Mary, are you ready?
Yes, thank you. So hi, everyone. Today I'll be discussing some of the results of our saltwater intrusion monitoring near Dover, Delaware today. Next slide. Just to orient everyone, Delaware is the state shown outlined in red. It's found in the mid-Atlantic region along the east coast of the US and is part of the Delmarva Peninsula, which is composed of Delaware, Maryland, and Virginia. It's bounded by the Chesapeake Bay to the west and the Delaware Bay to the east and the Atlantic Ocean to the south. Most of the land on the Delmarva is harvested cropland, making it a very important agricultural and economic region. Next. Delaware is the lowest lying state, and with the exception of the northernmost portion, most of the land is within 60 feet or just 20 meters of sea level, making most of Delaware very vulnerable to sea level rise. Additionally, the mid-Atlantic region is experiencing up to twice the global average rate of sea level rise because the land is still subsiding due to isostatic adjustment from the last glacial period. Dover is the capital of Delaware. The city area, which is shaded in purple, is surrounded by agricultural lands shown in orange. Both the city and farmers rely on groundwater as their primary source of fresh water. So when you're combining the low elevation of Delaware with its proximity to the coast and competing groundwater demands, the Dover area is at high risk of saltwater intrusion. So as part of our assessment, we have focused our field monitoring on the farmland to the east of Dover, since as you can see, it is adjacent to tidal wetlands, which is shown in green. And during high tides, these wetlands are fully inundated from water from the Delaware Bay. To help you envision the processes I'll be discussing, these diagrams kind of show how saltwater intrusion is or may be occurring in this area. The schematic on the left is depicting subsurface intrusion, which is probably more commonly thought of when you think of saltwater intrusion. Here, the interface between saltwater from the ocean can migrate landward into the freshwater aquifer, usually due to sea level rise or increased groundwater withdrawals. This is often a relatively slow and gradual process. On the right is an intrusion mechanism, which we are currently seeing in the Dover area that occurs on a much shorter time scale. So some of the farmers use irrigation ponds to water their crops. And while these ponds are permitted as surface water, the bottom of the ponds penetrate into the top of the shallow aquifer, and thus making the pond more like a very large open pit well and serving as a direct connection between groundwater and surface water. So all these ponds are connected to adjacent tidal marshes as well, either by a dug path or an installed conduit. This connection is meant to act as a drain to prevent the pond from overflowing during periods of heavy precipitation. However, due to climate change and specifically sea level rise and storm surges, these drains have begun to act more as pathways for saltwater intrusion. So while its salinity spikes from high tides only last as long as the tidal cycle, during periods of sustained higher water levels, especially during storm surges, salinized water cannot drain out from the pond into the marsh. When we have rising sea level and more frequent and intense storms, the residence time of the saltwater in these ponds may increase to periods which would allow for the saltwater to migrate into the surrounding aquifer, contaminating the groundwater. So we have installed several sensors in ponds, marshes, and wells that record water and conductivity levels every 15 minutes. We are using conductance as a proxy for salinity, and as reference, about 1,000 microsiemens is 0.55 parts per thousand salinity. So here's Site A, one of the farming operations which uses a pond for irrigation. The color of the map symbols match the graph colors, just so you're aware. So as shown as the graph, abrupt spikes in conductance correlate with high tidal events, and conductance levels increase during growing season. So the farmer here has actually previously reported he would experience minor crop loss due to elevated salinity in the pond, but he was never very greatly concerned about this. But during the last growing season in 2019, salinity levels in the pond were sustained throughout the irrigation period, which increased crop loss to such a level that the farmer took some action. And so in early spring of this year, the farmer installed a dam to separate the pond and marsh. There's a conduit that runs through it, but there are riser boards that allow the farmer to control the water levels in the pond and to keep the saline water from the marsh out. And so as you can see during this past summer, so I'm not sure if the slides are moving forward, go back, thanks. So if you see during this past summer, the salinity levels remain much lower than in 2019. So now next slide. So at Site B, which is just below Site A, it also uses pond water for irrigation, but again, these ponds penetrate into the shallow aquifer, so it's essentially groundwater that they're using. And here there's a berm that separates the pond from the tidal marsh, but there's an open conduit, just a pipe running in between the marsh and the pond that allows water to flow both ways depending on the heads in each area. We installed 2 monitoring wells in the berm that separates the pond and marsh in 2018, one to a depth about 25 feet and the other one to about 60 feet, but they are both screened within the top aquifer. So unlike Site A, Site B has not experienced any prolonged salinity events, but only the very occasional short-lived spikes due to tidal events. However, in last October, when Tropical Storm Melissa passed off the East Coast, it did so during high tide and caused some of the highest levels of tidal surges seen since Hurricane Sandy in 2012. The effects of Melissa can easily be seen in the conductance graph on the right, at the bottom. The surge caused conductance levels to spike to about 28,000 microsiemens in the marsh, and that water bled into the pond shortly after, and salinity levels remained elevated in the pond for several days. And that allowed for the saline water to enter into the aquifer, reaching the shallowing monitor after about 10 days, and eventually the deeper monitoring well after a couple months. So even now it has been a year since that storm has passed, and salinity levels have not recovered to what they were before the storm. Next. So the last site is one that actually uses water from 3 irrigation wells. Those are marked as the red triangles on that map. We installed sensors in several of wells on the property. Some are test wells adjacent to the pumping wells, and then we've also installed these shallow and deep wells. The data being shown are from 2 of the deeper wells that are both constructed to and screened to about 70 feet, and the 2 shallow wells have depths to about 10 or 12 feet. Only shallow well 2, located on the edge of the marsh, has shown elevated conductance levels. Next. So if we, back. Yeah, if we blow up the axis to look at the other 3 wells, we can see that deep well 2, however, does exhibit a tidal signal in its conductance levels. Next. So what this is starting to show us is that we are seeing impacts of climate change on saltwater intrusion. The rising sea level is pushing saltwater further in during high tides and storm events, and the higher water level slows the drainage time of the saltwater off the land, potentially reaching residence time that could promote marsh migration into cropland. And if saltwater is pushed into irrigation ponds and cannot drain back out quickly enough, the saline water could migrate into the shallow aquifer and salinize the groundwater. All of this could result in huge economical losses from decreased crop yield. And though we haven't seen strong evidence for widespread subsurface saltwater intrusion yet, I'm starting to develop a 3D variable density groundwater flow model to assess when that might occur and what level of risk that may pose. Next. With that, I'll just acknowledge all the organizations that have helped fund this research.
Mary, thanks very much for your presentation. We have time perhaps for one question or so before we move to the next speaker, and we can take more questions obviously in the plenary. There was a question that came from the audience around the boundary conditions and what kind of boundary conditions you were considering in this. I mean, are you focusing on the it seemed, the evidence that you presented, that it was the storm surges that are delivering the most salt at the moment, rather than perhaps some slow rising change in sea level. How might that be considered in your? Is that something that you're looking at in your modeling, the business between a slow rise and the episodic storm surges?
I'm not looking at storm surges in particular with this model, but I do include the irrigation ponds and tidal streams that could act as pathways and might be playing around with the salinity levels in those surface waters to see how long it may take to migrate into the groundwater for that.
Okay, thanks. I think we'll continue this this conversation in the plenary, but thanks very much. The presentation was very clear. We'll move, I guess, to the next speaker now. And Renee, could you introduce the next speaker?
Yes, the next speaker is Robert DiFilippo. Robert is a doctoral scholar in water resources in developing countries, affiliated with the Water Engineering Development Center in the School of Architecture, Building, and Civil Engineering at Loughborough University in the UK. Robert, are you ready?
Yes, I am, and thank you. I'm here to present the Interdisciplinary Freshwater Lens Assessment Protocol for Karst Islands, as conducted on Bantayan Island in the Cebu Province in the Philippines. This research aims to assess the impact of saltwater intrusion on Karst Island water resources through the application of an iterative non-invasive hydrogeologic characterization, and social science-driven assessment. The research also identifies the impacts of climate change and political will on groundwater resources through the lens of a remote island community who suffer from water scarcity. Next, please. The Vasaya Basin is located in the central portion of the Philippines, of the Philippine archipelago. And this is bound by two convergent plate boundaries on the east and west, and a left lateral fault that runs down the length of the archipelago. And Bantayan is a carbonate island of 113 square kilometers and has 3 primary local government units, one to the north in Madridejos, Bantayan in the central portion of the island, and Santa Fe to the southeast. The lower image shows a profile viewed from the east, the windward side of the island, the north point of Madridejos, a long terrace extending up to the zone of recharge at about 82 meters above sea level, and the south point tapering down to Santa Fe, which is the primary tourist location. Bantayan has a population of about 145,000 residents, and over 180,000 tourists visit the island on an annual basis. Next slide, please. The freshwater lens assessment protocol was developed for this research and includes a hydrogeologic characterization that evaluates remote sensing, imagery, geologic mapping, hydrogeologic assessment of pumping wells on the island, 4 different tidal studies, and underpinning the geologic and hydrogeologic characterization was a groundwater monitoring and sampling program that was conducted over a 12-month period at 4 different intervals commensurate with different seasons. There was also a stakeholder interaction program that included 37 well surveys issued, 74 laboratory reports issued to these well owners, and semi-structured interviews that were conducted, actually triangulated through the national, provincial, and local government units. This data, when assimilated, was formed into an observational model of the freshwater lens beneath the island, and the data was then put into a groundwater vulnerability indicator assessment to determine the likelihood and vulnerability for saltwater intrusion occurring on the island. Next slide, please. Geology is significant in understanding the morphology and mechanisms of saltwater intrusion. So the geologic analysis began with a pencil sketch for this island since there was no mapping available, followed by a differential GPS survey, which formed a digital elevation model, which is central to this slide. LiDAR data was obtained from the national government, and that helped fine-tune the DEM. And then what produced was the first geologic map of the island. Eolianite deposits are found atop 6 different calcareonite units that are bounded by some lagoon deposits and then some new marine deposits along the flanks of the island. The structural discontinuities, some of the faulting that was observed in some of the fractures, certainly had an impact on groundwater flow, which will be shown in subsequent slides. Next slide, please. Here's an example of some of the data output. Here's a chloride isoconcentration map to the left, taken during the rainy season, and you can see the 250 milligram per liter contour interval to the top of the slide and bounding the coastal margin, certainly from the cause of tidal forcing. But what I want to point out is the incision of the 50 milligram per liter contour interval in the south central portion of the island, where we can see salts extending into the island center along a structural discontinuity, also in the proximity of 2 active pumping wells, wells 23 and 24 in the lower portion of your slide. The groundwater gradient is radial, starting off in the recharge zone. This is on the right side of the slide. We can see a 4 meter above sea level groundwater mound that radiates from the central portion of the island. To the north, you can see the wells in red, the dots in red are production wells. That freshwater lens has been bifurcated and pinches off to the north. Predominantly, groundwater flow is to the south under the influence of a series of other pumping wells through the center of Bantayan, extending down into the southeast in Santa Fe. Next slide, please. A groundwater abstraction and groundwater balance was completed for the study. Groundwater abstraction data was applied from local municipalities and self-supply estimates were conducted. About 43% of pumping is done from the LGU and 55% is done from self-supply estimates. And a small portion of that is in the commercial abstraction. We're pumping about 2.5 million cubic meters per year from this freshwater lens. The lower slide shows the recharge, the groundwater balance analysis. Recharge was calculated based on precipitation. A factor of 0.26 was applied to that precipitation value to take into account evapotranspiration. And then looking at the area of recharge, instead of using the 113 square kilometer estimate of the island, that was modified to 85 square kilometers based on a buffer zone where we know there's saltwater intrusion occurring due to tidal forcing. What's evident in this slide is that in 2010, we have about a 24% ratio between recharge and discharge. And that's of course due to a low precipitation during that time interval. 2018, the last set of bars shows a much higher precipitation value and only a 5% ratio between between recharge and abstraction. Next slide, please. The observational model completed is actually used as a tool to communicate some of this information to local stakeholders. This was an opportunity really to share with the stakeholders what's actually occurring beneath the island and the morphology of the freshwater lens. What I'd like to point out is the blue dashed line indicates the thickness of the freshwater lens based on Geibin-Herzberg. And you can see that's during the rainy season. The aqua dashed line is during the dry season. So you can actually see the expansion and contraction of the freshwater lens between these two seasonal extremes. Groundwater elevations are also noted along the image. And you can see a slight mounting occurring in the interior of the island at the zone of recharge. Next slide, please. So the variables that were identified in the freshwater lens assessment protocol are listed on the left. This is a groundwater vulnerability indicator assessment model. And the intention of this model, again, is to communicate some of this information to our stakeholders. When you look at the primary variables, geology, hydrochemistry, and tidal forcing, they're relatively static variables. They have a set of outputs which really characterize the hazard. And then beneath that, beneath those primary variables, you see well field management, land development, and groundwater use and recharge. Those are considered more dynamic variables in terms of how the well fields are managed. Again, you have input variables, output variables. Trying to understand the context, there's 3 different stakeholder groups that were analyzed as part of this research. Through interviews, certain mediating variables became apparent, such as political will, regulatory policy enforcement, attitude, engineering capacity. Those mediating variables can impact the vulnerability for saltwater intrusion. So there's a bit of a feedback loop, the orange line that goes back to those dynamic variables. If you modify well field management by reducing upconing, you can alter the vulnerability for saltwater intrusion. Taking at its face and based on the data that I was able to collect, I was able to designate 3 different risk values: high, uncertain, and low. You can go to the next slide, please. And these variables are shown on this vulnerability indicator assessment map. So you can see along the boundary of the island, all these red dots. Of course, that's where we have passive saltwater intrusion occurring due to tidal forcing. What I want to point out are the yellow dots. Those are the ones where we have uncertain, where saltwater intrusion was identified during the research intermittently. Some of those areas are along structural discontinuities. Some of those areas are proximal to pumping wells. We see upconing and the effects of saltwater intrusion migrating within those wells.
Robert, can you wrap up in 1 minute?
Yes, next slide, please. And thank you very much for your kind attention.
Well finished, Robert. Thank you. I think, do we have? I'm just trying to get a quick check whether we've got time for a question. I think, Robert, we're going to move to the next speaker and we'll cover the questions in the plenary. But thanks very much for your presentation. Okay, well timed.
Very good. Thank you.
Renee, could you introduce the next speaker, please?
Well, I will, but before I move on, Robert, I understand that I mispronounced the name of your university. Would you please pronounce it correctly for the record?
It's Loughborough.
Thank you very much.
You're very welcome.
Our next speaker is Carolina Martinez Salvador. She is a postmaster scholarship holder and research assistant at the Universidad Nacional Autónoma de Mexico. I hope I pronounced that correctly.
Yeah,
if I didn't, please correct me.
So pretty. That's okay.
Okay. All right, Carolina, over to you.
Thank you very much. Thanks for the presentation and good day to all. On behalf of Dr. Norma Lopez and myself, I would like to discuss some remarks related to our ongoing research at the Geotechnics department. Next, please. This talk presents some results that are embedded into a much larger project that at the core aims to understand the spatial relationships between environmental pollution, mainly groundwater, mining activities, and aquifer status. We basically built the first snapshot of an aquifer vulnerability national map by using GOT methodology for the 653 aquifers the country is divided on. We integrated public access databases and technical reports. We do acknowledge, of course, the risk of overestimation and oversimplification of reality, but the final aim is to provide decision makers with easy tools to use to make calls when water allocation is at hand. We did this because Mexico has a huge mining sector that provides employment to around 2 million people and participates in the GDP with around 4% and on the rise, while also finding social nuances. Mexico is the first place in the Latin American region with socio-ecological conflicts that are related to mining activities, usually for environmental or water allocation concerns in the local communities. Next, please. So with having all this at hand, we took upon building the vulnerability index using GOT methodology. We use that methodology because it's a tool recognized by the national legal framework, particularly when a mining project needs environmental clearance. First, we built the index by integrating databases and technical reports, all remotely accessed due to the sanitary emergency that we are currently on. And we did a spatial comparison with two previously estimated indexes by the Water Council, we call it CONAGUA, be they vulnerability to climate change and water stress maps. And finally, we ask ourselves if stakeholders, the private companies, were actually using the vulnerability tools mandated by law in their reports, and we got access to environmental technical reports made by private stakeholders to see at what extent they are taking into account the vulnerability of the aquifer. Next, please. So, as you know, the GOT index stands for the evaluation of three physical properties of the aquifer, be they G, groundwater occurrence, that in the case of Mexico and with the estimations that we did, implies that most of our aquifers fall within the unconfined category, because either they are, or in case of lack of information, they needed to be overestimated. Then O, overlying lithology, that although quite rich in our country and heterogenic, on a class basis, using the GOT methodology, classifies as same as metamorphic rocks. And finally, depth to water, that in at least 60% of the aquifers in the country, we have found levels less than 5 meters depth. Finally, we classify it by using the suggested scale by the authors of the methodology. Next, please. So once we have the index estimated, most aquifers are classified either as moderate or low vulnerable towards pollution, and just in 7 cases, they ranked as extreme. One of them, it's the Yucatan Karst aquifer, extremely vulnerable due to its karstic nature, and it's an interesting spot to go on with further studies. But given the design of the index, in some cases, we did find cases that stand up because they have been labeled as overexploited by the CONAGUA, and yet they are located in the low vulnerable categories when it comes to pollution. This is a normal outcome given the GOT design, because of the drop of the water level when aquifers are overexploited reduces the drop in vulnerability classification, and yet is quite counterintuitive. Next, please. So, when the GOT results were especially compared with the existing vulnerability to climate change maps, some things can be said. First, although vulnerability to climate change is estimated on a municipality level, and an aquifer might be drawn within many municipalities with various degrees of vulnerability, most extreme or highly vulnerable aquifers towards pollution are also at the same extent vulnerable to climate change. A noted exception, of course, was the mentioned Yucatan aquifer that, as seen, ranked as extreme towards pollution, and yet most of the municipalities within the karstic system seem to be low when we assess climate change vulnerability. Further studies, of course, are needed and may arise from that spatial comparison, and we will be looking forward within the research that we are currently conducting. Next slide, please. So finally, when it comes to the actualization of vulnerability concepts within the real projects, only 6 out of the 194 environmental technical reports that we were able to access included the vulnerability estimation. That means that only 3% of those tools included the vulnerability conception of the aquifer, which might imply lack of knowledge. We don't want to see ill manners within that fact, and a needed of awareness into the tools, both at the private level, but also at the authorities level, that in most cases approve projects with or without the vulnerability assessment. We are looking forward also to regionalize and estimate the climate change index by ourselves and to increase resolution of GOT estimations to a mining polygon level. A mining polygon level is the area where mining activities are authorized, the concessions are given by the state, and mining activities might be able to be conducted in that place. And we would like to do that in order to explain some disparities in the areas between indexes. And finally, one of the main outcomes so far, and it's been building upon, is that we built the first national vulnerability map of aquifers using the GOT methodology. And although it requires more resolution and refinement, it is a first step towards raising awareness when it comes to vulnerability of aquifers, especially in the realm of a controverted and complex topic as mining is. Next slide, please. We would like to thank the organizers for the efforts, the feedback, and the opportunity to share some remarks. And here we have our contact data, because we would like to share our databases in GitHub, in a GitHub repository, in the aims to contribute to open science and collaboration. Any feedback you may provide, please feel free to send us a message. Thank you.
Thank you, Carolina, for your presentation. Very clear and well on time. We do have time for some a question or two at this stage. Perhaps I'll take kind of chair privilege at the moment. I don't see a direct question in the Q&A. So you mentioned it looks like a fantastic amount of work that you've done, a huge compilation exercise. What can you give us a sense of what these vulnerability assessments are now going to inform? What kind of decisions might local, regional, and national governments now make based on the kind of assessment that you have now done? I can see there's an raising awareness component to this, but is there something more that this might inform?
Yeah, of course. I know that it seems a little bit extreme sometimes to say it completely no to mining projects in some areas because of the importance economically wise and labor wise. But we aim that at least these tools help decision makers to say, okay, in this area, we have all of these indicators topping one each. You have one indicator towards vulnerability of pollution. You have we have done a lot of work when it comes to arsenic concentration. That is not shown here, but we have already done it also in a national scale. So by combining a lot of geospatial indexes, we aim to for the authorities to say, okay, let's space a little bit and think over if, especially in areas where there are a lot of social conflicts due to mining, if there is like if there is a rationality behind accepting the project, or if the project needs to be implemented in the area, how many measures we can actually implement to protect the aquifer. We want for the authorities to have a lot of tools to strengthen the protection measurements. Maybe not to cancel projects, but to be very, very clear and strict when those projects are being implemented, and monitoring constantly, and being really, really on the look into the projects.
Thank you, Carolina. That was very clear. Thanks for your answer. Excellent. We're now moving to our plenary session. We've got just a little under 20 minutes. And as I indicated earlier, I cut off Professor Scanlon a little bit early. So what I thought we would do is we would start with some questions. She was the first speaker. We'll start with some questions associated with Bridget's presentation. And then we will move to a kind of more general plenary where we take questions for any of the presenters. So please all stay on ready to contribute. So Bridget, Renee, perhaps did you want to select a question from this, or would you like me to go ahead in the first instance?
I think you're very good at asking questions, Richard, so I'm happy to defer to you.
That is very kind of you. I will go ahead. So Bridget, one of the questions that was taken from David Eduardo Guevara-Polo, he was asking about, to what extent in your analysis of the changes in water storage, what role do climate oscillations like El Nino play an influence in groundwater storage? And to what extent might these be worth studying to better understand how groundwater storage may change in the future?
That's an excellent question, and I think in some areas El Nino, ENSO is very important. In other areas, not so important. Pacific Decadal Oscillation or North American Oscillation, all of these cycles, I think it's important for us to consider them and their role. I know in the Central Valley, they have tried to link the wet and dry climate cycles to El Nino, but it didn't really, there wasn't a very good correlation. And then, in the Central Valley, it seems like atmospheric rivers are very important for ending droughts, and we're now starting to look at atmospheric rivers in Texas and to see how important they are. And we've looked at El Nino in the past in the Gulf Coast region in the US. El Nino was very important, and so I mean, my main message is, we have these wet and dry climate cycles. How can we manage them? And so it was like focusing using surface water during wet periods and just limiting groundwater mostly to dry periods. So I think we need to understand the controls on these. Thanks.
Okay, great, Bridget. Thanks for that. A follow-up question from Martin Shepley was around, he asked sort of a bigger picture question. He was saying, conjunctive use has been around, I'm just reading his text, conjunctive use has been around since the 1970s. So why has the idea of using surface water and groundwater conjunctively, why do you think, Bridget, maybe it's not taken off? Why are we talking about, why is this sort of new in 2020? Go on.
Well, I mean, I don't think it's new. I mean, and I think, oftentimes with managed aquifer recharge, we say it has to be intentional and we've managed it, but the aquifer cannot distinguish many of these factors. If they get water, they respond. If they don't, they decline. So I mean, we have long-term regional groundwater models showing when they use surface water in the Northwest that they had big increases in their groundwater storage. And I think maybe Alan McDonald has seen this in the Indo-Gangetic Plain, you know, when they had the irrigation canals and a lot of surface water use, that the aquifer was building up. So I think the difficulty of using both surface water and groundwater is the cost of maintaining 2 irrigation systems. And I know in some of these managed aquifer recharge systems in the Central Valley, they price the water so that they can maintain both systems and use the surface water when it's available. So, and there's a lot of logistical issues. People get accustomed to using one or the other, you know, and so it's those sort of factors, I think, that impact, you know, whether surface water and groundwater are used. For example, in Arizona now that they've had a drought for quite a while, the state is paying some of the irrigation farmers to drill new wells because maybe they haven't maintained those wells, you know, during the period where they were getting the Colorado River water. So it's kind of logistical issues, and a lot of our concepts nowadays are not new, and some of them are historical, and so we're just reinventing the wheel sometimes.
Sorry, thank you for that, Bridget. We'll move. I guess. Well, actually, I had a follow-up question, Bridget, for you on this. It's fascinating to see. I almost call it a schism between the major aquifers that are in humid areas versus the major aquifers that are in dryland environments in the U.S. And you mentioned one thing in your analysis about amplifying and dampening and the choice of the source of irrigation. And I was just wondering. There's with the, if we want to call it impromptu or unmanaged aquifer recharge from surface water irrigation, what is, it sort of relies on an inefficiency in irrigation. And I guess I was just wondering, can you comment on the kind of information at hand around irrigation efficiencies from surface water versus groundwater?
So I heard Claudia Font mention this a long time ago for the Central Valley. She said, we want flood irrigation when we're using surface water, and we want drip systems when we're using groundwater, so that we can minimize the storage depletion. And, you know, you mentioned, you know, the difference between humid and arid regions, and, you know, why should we be growing all our food in deserts like the Central Valley, where we may not be in the future with the Sustainable Groundwater Management Act. So maybe using hydroponics in the more humid regions. And even as hydrologists, we never pick where we live based on how much water they have available, what's sustainable. We just go where we want to go. But Barbara Kingsolver said in her book that, or not in her book, but that she moved from Arizona to the Carolinas because it's a humid region. She had no business living in Tucson. So, so maybe living in some of these very arid regions. But I think, you know, that concept, so flood, and this gets into the flood managed aquifer recharge that they're pushing in California in the winter period when the crops are dormant, or even with vineyards and stuff. So Helen Dahlke and others. And I think that's a great concept, you know. So we're going to be much more innovative in how we manage these things, I think, in the future.
Thanks, Bridget. That's great. There was a question for Chinchu Mohan about the uncertainty analysis in the estimation of recharge. And I'll sort of try to loop a couple of questions together, Chinchu, that sure. You mentioned that one of the conclusions from your work is we needed to consider greater, increased forms of uncertainty to, I suppose what you were saying, to account fully for the magnitude of uncertainty in projections of recharge. And I suppose, just to play a little bit of devil's advocate here, if we keep expanding the envelope of uncertainty, do we begin to get recharge estimates that are plus or minus sort of 200%? And then does it become almost, how meaningful does that exercise become? What are your thoughts on that expanded analysis of broadening the envelope of uncertainty?
That's a really good question. So first of all, I didn't mean to say that include all the uncertainties, but what I'm trying to do with this work is to introduce that there is an uncertainty that exists there, which is not being addressed, and it is equally important as the other uncertainties which we are addressing. I totally agree with you, Richard, that if we try to include all the uncertainties, it's going to be like peso minus 250. So which is not good. So there should be a fine line to say that how much uncertainty we need to include and how much accuracy we want the results to be. So all the intention of this work is to say that if you want to include, or if you want to make a reasonable estimate, you have to include like more uncertainty. But sure, I totally agree that there is a trade-off. Like it's kind of like a trade-off line where you have the uncertainty and you have the range, and which one you want to go with. Yeah.
Okay, thank you for that. There was another question. Sorry, that question, by the way, was Mariana Soli who asked that. And another question from David Eduardo Guevara Polo. He's asking, he's saying, look, given the asymmetry that you were projecting in recharge estimates in different parts of the world, do you have any, what kind of global cooperation do you think should be encouraged to tackle the impact of this asymmetry and imbalance in projected groundwater recharge?
Yeah, so my personal opinion for this is we all have a shared responsibility for protecting the groundwater, irrespective of whether we are in a wet region or a dry region, because it's very evident from several studies that the fruits of the dry region is not enjoyed by just the dry region people. It's spread all over the world. So if we look at the virtual water trade, then we can see that the products that are produced in the water stress region are maybe shipped to another place, and they are actually reaping the benefit. And also most of these regions are transboundary aquifers. So I would say it's a shared responsibility for everyone to take care of every groundwater hotspots.
Okay. So this is a bit of a climate justice argument here as well, isn't it? Yeah.
Yes.
There was, I believe, another, there was one question also about to what extent in your analysis were you considering large-scale controls on climate variability in your GCM? So things like ENSO and other large-scale forms of controls on climate variability, are they considered in your analysis?
As of now, no, because I'm using a simple precipitation and evapotranspiration dependent model. But there is always a plan to like extend analysis to see more of the drivers.
Okay, great. Yeah. Thanks very much, Chinchu, on that.
Thank you.
We have a question from Jason Gabriel Pinza for Robert. He was wondering, to what extent, Robert, were you able to account for double, or as he says, triple porosity of karstic geology in your intrusion model? Yeah, so the double and triple porosity dimension of karstic geology, to what extent is this considered in your intrusion model, Robert?
It wasn't actually evaluated as part of the model. The model was really based on groundwater elevation information and basic Geibin-Herzberg analysis to determine the thickness of the freshwater lens, and looking at the hydraulic head and seeing how the morphology of the lens would change. The geology, the calcarenite, I mean, it's highly karstic and was really considered almost like a porous media uniformly across the site. And of course, where there were structural discontinuities, as that one image indicated, you can begin seeing how flow is controlled by those structural discontinuities. But I just want to point out that over 80% of the wells that I evaluated were hand-dug wells. 20% of the wells I was using were mechanically drilled wells. And of those 20%, I only had access to 2 of those wells for actual groundwater monitoring. And the wells were very shallow penetrating.
Yeah, there was one other question about, there was one question from Nyo Kang about the use of LiDAR and object-based image analysis for mapping. I guess he was wondering how you reconciled those two. Do you want to maybe just speak a little bit to how that was done?
The development of the mapping was obviously quite challenging. Conventional GPS to differential GPS. Even with differential GPS, there were many points of interference and precision issues. Fortunately, I learned to create some strategic relationships with academics in the Philippines to help in support of the differential GPS. Being a foreign researcher, I was unable to access government LiDAR data until reaching a relationship with the University of the Philippines that was able to get me the LiDAR data. That happened on the 11th month of my time in the field. So by the time I got back to the UK and was able to start assimilating all this information, the LiDAR data really helped in understanding some of my field geology mapping that I did, and then looking at the LiDAR data and how it corroborated with some of my field observations, and really assisting in that process.
Okay, great. Thanks, Robert, for that. Question for Carolina. And they were wondering to what extent you were able to account for the natural background chemistry of the groundwater in, say, mining areas. So when you're looking at a vulnerability assessment related to pollution, to what extent did you have information on the background or baseline quality of the water or chemistry of the water? Can you comment on that?
Sure. The God index does not account for any kind of a specific pollutant, but we actually have done other research, and we have compiled databases from CONAGUA that include concentrations of arsenic or iron within the water. And the way that we are accounting for natural occurrence is by locating the areas where there has already been studies that suggest that, for instance, the arsenic is naturally occurrent. For example, in the Comarca Lagunera, at the center of the country, a little bit in the north, in the Baja California Peninsula, we have we have a lot of work in, not us, like we have just checked some researchers that have pointed out to places where the natural occurrence, for instance, of arsenic, it's been detected. So those places are already marked in our databases. So we are not contributing or not linking, we will not be linking mining activities in those areas to groundwater pollution just yet. Like maybe we can do it with a modeling, numerical modeling with transport pollution, but not in this assessment.
Thanks very much, Carolina.
I hope I answered the question.
Yeah, well, as best you can. Well done, well done.
Thank you.
I think we'll just have I'll pass out, we don't have much time, so I'm gonna pass almost a final comment, which relates back to Bridget's presentation. It comes from Mike Jones, and it points out that very interesting points on conjunctive use. He said in England, probably in England, maybe not the UK specifically, but in England, the trajectory is towards reducing groundwater abstraction, which is seen to be unsustainable, and as a result to reduce the current conjunctive use of groundwater and surface water. And so I guess kind of a bit of a lament about, are we moving in the right direction in England around water supply resilience by reducing groundwater abstraction rather than using it in a more equal conjunctive manner. I think that wraps up our session. And I'd like to say thank you to all of the presenters. It was excellent. Everybody kept on time, was very clear. And a big thank you to my co-chair, Renée Martin-Nagle. So thanks very much to everyone. And any of the questions not answered, we'll try to get to these by email and other methods. Okay, thanks very much.
Thank you.
Thanks to you too, Richard.
Thank you.